Hello, the AX344 here. Today we're gonna continue with the series. I'm gonna make it a series because yes, I just want to. So last time we left off was me showing this off, me showing this off a bit. I've upgraded it, as you can see. It's all done-ish. I mean, like, it's nicely done. I haven't finished it, of course, but basically this is our program storage. This is our thing to program it, basically, and we can also hook it up to the I/O. So that's basically for people who haven't seen this yet, or the previous one even. One thing that I'm going to change about this was going to be my version 4.0 computer. I'm going to scrap it, make a 5.0. So basically the only difference is I'm adding another line, another 4 bits in right here. So I'm going to move this back a bit, add 4 more operations, just to make sure to have your, instead of having to program these with ROM, you can actually program them in the thing. So it means instead of having a computer to instead of making a computer be able to program another computer, you can make a computer program another computer that can program that computer back again, which is quite useful. I don't really know why you'd want it, but I know. Pretty cool. And the I/O I'm completely redoing as well. So last episode I did show off, so I'm basically adding to this 32-bit instruction set. Last episode I showed off this I/O. I'm not sure I've built it over here, yeah. And it's fairly, it works. I mean, it works, but I mean, it's not the most efficient data protocol. So this episode, I'm just saying about my new data protocol. I haven't actually built it yet, but I've got it on a piece of paper. Let's try and find it under the list of all my stuff. Oh, these are upside down, that's why. So, new data protocol. And also, I was previously going to use a modified version of my 50 subscriber ALU, which I've used in here. So I was going to use a previously modified version of that I did upgrade, but then I'm not going to use it at all now because I think I'm just going to build a whole new ALU because that one's kind of inefficient. It lacks certain features and it's big and bulky. So, alright, let's find the thingy. Alright, so here's my serial bus data. So, the new protocol scraps these last 4 lines, so they're no longer a thing, and so you only have to transmit 12 bits. This makes it much more efficient, and the actual address is completely rewritten. So 000 does nothing, 001 saves the data, 0010 sends the 8-bit line address, which basically was previously this, but now I'm just going to make it, instead of having a separate thing, I'm just going to keep it all in one data transfer. So you don't need a separate thing to transfer the line address. You can just transfer it on the main data line, just specify that it is the data address, and that works pretty well. So that means you get 8 bits of addressable program memory, which means you can have up to 256 lines of code, and which supports a 96-bit instruction set, because number 3 would be clock on off, just to say I want the computer to turn on or not, and the rest of them are basically send 1, send 2, send 3, send 4, send 5, and all the way up to send 12, and that basically sends 8 bits with the address just 1, alright, and that, or 2 or 3, whatever it is basically, and it's very efficient, and it means you can send up a lot of data. So as I've said, you can have a 96-bit instruction set and send 256 lines of code, but if you use one of your sending commands as also a line address, you can have an 88-bit instruction set. I know it's less, but it does mean you can have 16,384 lines of code, which I'm not sure why you'd ever need that. I'm not sure who'd ever even build that, because that's a lot. That's a lot of code, and seeing as just this is one module, and just the entirety of this is 16 lines of code, and of course that's only 1 bit of instruction set. To get 88 bits would be 88 ones of these in a line, and 16,384 of these small large modules, all stacked all the way over there, and you could always do it on top. I mean it just opens a lot of possibility, and I know it's still an 8-bit thing, but if you ever wanted to upgrade it, all you had to do, add another 8-bit address, 8-bit data here, and then you add another 4-bit data address over here, and it makes it fully upgradable, and you can use it to future-proof as well. So it's very future-proof, because it means future computers that transmit 32 bits at a time will still have the upgradability, which makes it such a better data transfer than the previous version. And I'm definitely going to be using this for this new computer. And the only difference to the architecture that I'm going to make is, instead of the data transfer all being ROM, it will be RAM instead. So it will be built in, so you can program a computer to program another computer, basically, which I think is pretty cool if I don't say so myself. So yeah, that's basically that. What else was I going to say? Yes, I'm going to build a new ALU, because that one's kind of trash. Either I'm going to build a whole new one on my own, or I'm going to use Nubosaurus, his design for his compact ALU, and that's a very good design, by the way, so I suggest you check out his video. Yeah, just search up Nubosaurus, noob_saurus 8-bit, not 8-bit, just compact ALU, and it should come up. It's pretty cool. And yeah, so that's what I'm going to do with this computer. And as you can see, I've already started work on it. I've made the program counter. I'm making the actual programmer for it at the moment with this over here. And of course, since I'm upgrading it, I'm going to break these and replace them with 4 of these lines. So I'm basically just going to copy all of this and paste it over here. Pretty simple. And all it means is I have to extend this by a bit, and that's fine. I don't really care. I think it's worth it. The only problem that makes is that instead of sending the entire instruction set in 5 lines of code, you now have to send it in 6, because it used to be 5 lines of code, because you have 4 lines of code for each 8 bits of the instruction set, because 32 can divide by 4, so you have 4 times 8. So you have 1, 2, 3, 4, 5, 6, 7, 8. That sends, and then your first one would send the first 8, second one would send the second 8, third one would send the third 8, fourth one would send the fourth 8. Basically, that's how that works. But yeah, now it would have to send the first 8, second 8, third 8, fourth 8, and also fifth 8, or basically just these 4, because it's not gonna be, it's only 4, not 8. I could increase it, but not at the moment. Unless I find something useful to increase it with, I'm not going to increase it. I'm just going to keep it 4 bits. So it'll be a 36-bit instruction set, and that is going to be fairly cool. And hopefully this computer with a new ALU, that either I'm going to use Nubosaurus's design or I'm going to make my own design, it should be very fast, hopefully, because of the way I'm going to be using a very similar architecture to that one over there, and it uses RISC, so it should be, the instruction set is a RISC instruction set, so a reduced instruction set, which means you don't do complex operations. So you basically, a very good example of RISC versus CISC, CISC is the complex instruction set, that means it does like multiple things, is basically RISC, say you wanted to convert to BCD, a RISC instruction set
you'd actually have to program a BCD conversion out on each individual line to do that. Whereas a CISC instruction set, all it would do, it would have one of the instructions would be, oh, convert to BCD, and you could just go on like that and it convert it to BCD. Like, I'm not sure why you'd use BCD, but maybe for a display or something, but yeah, that's basically a good example. So yeah, some of the things that I'm going to add are multiplexers to these, just to make sure conditional branching works. The conditional branching that I'm going to be using is if ALU output equals 0, if the ALU overflows, or if the ALU is a negative number. There's a kind of simple, whoops, there we go. And that is quite simple instruction set that you can use. I mean conditional branching. So yeah, this has been an alright update video, I'd say. It's a lot of progress to this, and hopefully I can make a really good ALU. I'm going to try and make it, I'd like to make it 2 wide, tileable, but I'm not sure that's possible. The design that Nubosaurus had was 2 wide tileable. I can try and make it 2 wide tileable, but I'm probably going to make it 4 or 3 wide tileable. Just, yeah, 4 wide tileable. So these would be input A, input B, input A, input B. That's probably the best bet that I'm going to do. So yeah, I hope you liked this video, and that is bugging me. So yeah, hope you enjoyed this video on just this small update on what this computer will be. It's going to take a long time to make, of course, just because there's so much things I need to make. Like that computer I made in what, like 6-7 hours, that 8-bit computer. This is going to take like a few days for me. So a few days, I say, it's probably going to take a few weeks, because I want it to be a very, very, very powerful computer, just in like how many things it can do. And the best part about it, I want, is that is the I/O. I want the I/O to be the main feature, so you can program it with a different device, or you can get computers to program other computers. I think that would be super cool if I could do that. And I have the infrastructure to do so, I just need to actually make it. So yeah, hope you enjoyed this. Please like and subscribe. And I am out. Thanks for watching. See you later.